In this video, we're going to go through question 12 from the NESA Sample HSC Mathematics Extension 2 exam. Question A. On the argand diagram, the complex numbers 0, 1 plus root 3i, root 3 plus I, and z form a rhombus, and they've given us a diagram. Part I says find z in the form a plus bi, where a and b are real numbers. So here's our diagram, and here's our point here's our point z, which is what we're trying to find. Now, for that point z, we can draw in its vector representation. So here is the vector representation of z, and we can see quite clearly that to get z, we're going to add up these two vectors. The first one here in green, that's going from the origin to 1 plus root 3i, so this is 1 plus root 3i. And then we have this vector in purple. Now we don't know exactly what that is right at the moment, but we can think a little bit about it, and then we can just see that it's this vector here has been translated up to give us that vector. We know that this vector here is root 3 plus I because it's going from the origin to root 3 plus I, which means this is also root 3 plus I. And so our vector z, our blue vector, is going to be the green one plus the purple one. That's just simple vector addition. So we have 1 plus root 3i plus root 3 plus I. And we're adding two complex numbers, so we add the real parts and we add the imaginary parts. So the real part is 1 plus root 3, and then the imaginary part is actually going to be 1 plus root 3 as well. But of course we have to multiply that bit by I, and so here is our value for z in the form of a plus bi. Part 2. An interior angle of the rhombus theta is marked on the diagram. Find the value of theta. Okay, so I'm actually going to get rid of all this stuff here, just so we have a bit of a clear diagram to work with. We're trying to find this angle theta. Now we know that this is a rhombus, and there's a few things we know about rhombuses. Firstly, we know that opposite sides are equal and parallel. So these two pairs of sides are equal and parallel. We also know that opposite angles in a rhombus are equal. So that means that this angle here is equal to this angle there. And this angle theta is also equal to this one. So we can, if we wanted to, we can label this angle in here as theta. So we're going to use some of these properties, or these geometrical properties of a rhombus, to our advantage here. Now, the way that I would approach this is I would think that these two lines are parallel. So I'm going to indicate that by putting in two parallel, indicating that these are parallel. And that makes this line here a traversal. And we know something about parallel lines. We know that there's a lot of things we can do with angles. We know that this angle in here is going to be 180 or pi minus theta because they're co-interior. So I need to find a way to work out that angle in there. Okay, and hopefully you can see that this angle, maybe we should even label these. Let's call this point P and call this point here Q so that we have something to reference. We're doing part 2. So angle POQ, it's really going to be the argument of 1 plus root 3i, because that's this entire bit here. So it's the argument of 1 plus root 3i minus this little bit in here, which is the argument of root 3 plus I. So arg of root 3 plus I. So let's work that out now. Argument of 1 plus root 3i. That's going to be tan inverse of root 3 minus argument of root 3 plus 1 is tan inverse of 1 on root 3. So tan inverse of root 3, that's going to be 60 degrees or pi on 3 radians. And tan inverse of 1 on root 3 is going to be 30 degrees or pi on 6 radians. So overall, our angle in here, this angle, the one inside our rhombus, is going to be pi on 6. And so now we can use the co-interior angles add up to 180 degrees. This angle plus that angle in there is going to be 180. So we can say, therefore, pi on 6 plus theta equals 180 degrees, or pi radians. And so therefore theta is equal to 5 pi on 6. I suppose maybe here we should mention co-interior angles add to 180 degrees, or add to pi radians. Okay, if you just want to make sure that you're giving all your reasons, so a marker never has a reason to take a mark away from you. But that's our final answer. Theta is 5 pi on 6. Question B. Part I says, on the one diagram, draw neat sketches showing the subsets of the complex plane satisfying each of the relations. The modulus of z minus 3 plus 2i is equal to 2, and the modulus of z plus 3 equals the modulus of z minus 5. So we want to draw some regions in the complex plane, or you may have thought of them or heard of them are being referred to as locus or loci, since we have more than one. And these loci are in some standard forms. Hopefully you're able to recognize what they are. So the first one, we've got z minus, or the modulus of z minus 3 plus 2i is equal to 2, and that's a circle. So this here is a circle. Its center is at this complex number, 3 plus 2i, and we know it's at that complex number because we have a minus sign here. So if you were given a question where you didn't have a minus sign, you do need to factor out that negative. So the center is at 3 plus 2i, and the radius is going to be equal to 2 units. That's just reading it straight off there. So this is a circle, and pretty easy to draw that. The second one here, this is also a standard form, but it might be helpful if we rewrite it in the following way. Just like we were saying that we need to factor out a negative 1 here, we're also going to need to do the same thing with the plus 3. So this will be minus negative 3 equals the modulus of z minus 5. And so now we know that this is the perpendicular bisector of the chord which joins these two complex numbers, minus 3 and 5. So of the chord joining negative 3 and 5. Cool. Let's put this now onto our diagram. So let's deal with the circle first. We want to go to 3 plus 2i. So we go across 3 and up 2, and we get to this point here. And our radius needs to be 2 units. Now, I've got a nice grid paper here, so it makes it a bit easier for me to draw it. But even without a grid paper, I know that I'm going to have to just touch, my circle is going to just touch my x-axis here, because I've gone up 2 units and my radius has to be 2. So it's only chance that it has of touching is at that one point there. So let's go ahead and draw that in. And in an actual exam with pen and paper, it would be a really good idea to try and get as accurate a diagram as possible. Now I have the advantage of this nice feature on the iPad, which makes drawing circles quite easy. But I would really recommend having a compass with you, or maybe one of those things where you can draw circles quite easily. They're pre-cut circles. I remember when I was doing my HSC, I had one of those with me, and it came in very handy when I needed to draw diagrams. But do try to get the most accurate diagram that you can. Now, this is the point 2 plus 3i, so we should indicate that. And probably a good idea to also indicate a radius of 2 in that manner. So that's this part here. The next part we want to draw is this one. And we said that this is the perpendicular bisector of negative 3 and 5. So where's negative 3? Negative 3 is here, and 5 is sitting there. So 5, negative 3. And the perpendicular bisector, well, bisect means it needs to cut this chord in half. So the chord we're talking about is this one here. Needs to cut it in half, so that's actually going to go down the middle like this. So this is going to be our perpendicular bisector. It goes on forever, and this is at the point 1. Okay, and so this is we've sketched our 2 relations, and this is our final answer. Now part 2 says, hence write down all values of z which simultaneously satisfy both relations. So we want to find what values of z satisfy both of these relations, and that's obviously going to come at the point where these two loci intersect, our two curves intersect. And we can see that there's only really one point. It's at this one point here where they intersect. So what's the coordinate of this one point here? Well, it's got an x coordinate of 1 and a y coordinate. It's the same as this y coordinate, which is 2. So z equals 1 plus 2i is just our answer here. This is the only point which satisfies both of the relations. Now part 3. Use the diagram in part I to determine the values of k for which the simultaneous equations, the modulus of z minus 3 plus 2i equal to 2, and the modulus of z minus 2i equal k have exactly one solution for z. All right. So we're looking at, maybe let's write these two down as well. What do we have? We have the modulus of z minus 3 plus 2i, which is exactly this one, which is equal to 2. This is exactly what we saw above. That's our blue circle here. It's that one there. And now we've got something else, and I'm going to write this in purple because I'm going to draw it in purple. The modulus of z minus 2i equal to k. And we want these two to have exactly one solution. We want to find what value or values of k give this exactly one solution. Now, firstly, let's think about what this is. We already know what this one is. That's the circle centered at 2 plus 3i with radius 2. This is the circle which has a center at positive 2i. Center equals positive 2i. And the radius is k units. So let's go to 2i. 2i is here. And we don't know what our radius is. Our radius is k, but what we do know is that we want it to have only one solution when we're looking at both of these. So what it means is we want it to intersect our blue circle only once, which means it needs to be tangent to the blue circle. So that means that we have something like this. Okay, that's a possible value for k, right? K would have to be 1 unit here, and that would be possible. So we have, let's write it here, k equal to 1 is a possible solution. But actually there's another possible solution. There's another way that this circle centered at 2i could be tangent to this blue circle. And that's if it goes all the way around and touches just at that one point there. So that means that our radius would be 1, 2, 3, 4, 5 units. Didn't come up. 1, 2, 3, 4, 5, like that, all the way up to here. So we need a radius of 5 units. Now, let's actually draw it to see what it looks like, because it might be helpful to see. There's 5 units. If we go down to 5 there, go across to 5 and go up 5. 1, 2, 3, 4, 5. Okay, let's do our best to draw this accurately. We get something like this. So you can see that in this case, we're only touching it once. It's only touching at one point there, but it's another kind of circle that we could have. Okay, so this would also work. So a radius of 5 units would work. So these are actually our two answers, two values for k that would give us one solution when solving these two regions. Okay, I think a lot of people will find the first one and then forget about the second one. But there is that second one there. And you can see it clearly. There's only one point of intersection. And that's the end of part B. Question C. Find all the solutions of the modulus of e to the 2i theta minus 1 equals root 3, satisfying minus pi is less than theta is less than or equal to pi. Okay, so I think there's a few ways that we can go about this, but I'd like to show you what I think is probably the nicest way of doing it. It's a very algebraic approach, but it uses some good techniques and algebraic skills that you need to be confident with when dealing with complex numbers. Now, when I look at a question like this, I notice that we have some complex number and we're taking 1 away from it. So this is sort of something of the form, let's write it on the side here, z minus 1. Now, a lot of the time when we're dealing with something of this form, we want to resort to our half angle results, right? Because z, we can write it as cos plus I sine. If it's on the unit circle, of course, we can write it as cos plus I sine. And then to deal with this -1, we want to write it in terms of a half angle in order to simplify and get rid of that 1. And then we can write it in a mod arg form of some sort. But one of the really good things about the introduction of Euler's form, the exponential form of a complex number, is that we can do this quite easily by a little trick that we're going to use here. So what I'm going to do is I'm actually going to factor out inside my absolute values, or inside my modulus, I'm going to factor out e to the I theta. So it will look something like this. I factor out e to the I theta. From my first term, what's left over? Well, I will just have e to the I theta again. And from my second term, what would be left over when I factor out e to the I theta from -1? Well, that's going to be e to the minus I theta. And if you're unsure about that, we'll just think about it. If we multiply that by that, we get e to the 2 I theta. If we multiply these two together, we'll get -1. And this is equal to the square root of 3. Now, the advantage of doing that is we get this result popping out. And hopefully you're confident enough with your complex numbers to recognize this as some complex number minus its conjugate. And we know that that's going to be 2i times the imaginary part of the complex number. And what's the imaginary part of this complex number? Well, that's just going to be sine theta. So this is really 2i times sine theta. So I can rewrite that little expression in there as e to the I theta multiplied by 2i sine theta equal to root 3. And now I'm going to split this up because everything inside my absolute value, or my modulus, is a product. So I can split them up into the product of the moduli. So I have the modulus of e to the I theta multiplied by the modulus of 2i multiplied by the modulus of sine theta is equal to root 3. Now this bit here, the modulus of e to the I theta, well, the modulus of e to the I theta is 1 because this lives on the unit circle, so that modulus is 1. The modulus of 2i is really the modulus of 2 times the modulus of I, so that's 2 times 1, so this is 2. And then this part, the modulus of sine theta, well, we're not going to do anything with that yet. So let's continue. We've got 2 times, pen is starting to play up a little bit, 2 times the modulus of sine theta equals root 3. We can divide through by the 2, and we get the modulus of sine theta equals root 3 on 2. And to remove our modulus, it's like when we're removing an absolute value, this is going to be sine theta equals plus or minus root 3 over 2. And now this is something that is very easy to solve for us. This is an advanced, a 2-unit kind of question. So we should be very comfortable solving these. But we do need to be a little bit careful about our restriction, or our domain on theta. Theta is between minus pi, not including minus pi, and pi. So quickly we draw up a little axis here. We draw our all stations to central. So for the positive case, and I'll just take it one step at a time, you might not feel that you need to do this, but I'm just going to add it in just so people watching are 100% sure of what's going on. For sine theta equal to root 3 on 2, that means we're going to be in the first and the second quadrants because that's where sine is positive. So theta is going to be, well, when is sine equal to root 3 on 2? That's 60 degrees or pi on 3 units. So this is pi on 3 in the first quadrant. In the second quadrant, it'll be pi minus pi on 3, which is 2 pi on 3. For the second equation, when we're looking at minus root 3 on 2, that tells us we're going to be in the fourth and the third and fourth quadrants. Okay, but we're not going all the way around like this because that would now exceed our restriction of being less than pi. So instead we have to actually go in the opposite direction. So if we're sitting in this quadrant, it's going to be minus pi on 3, and if we're sitting in this quadrant, it'll be minus 2 pi on 3. So our answer for this equation will be minus pi on 3 and minus 2 pi on 3. And so overall, our answer will be theta equals plus or minus pi on 3 plus or minus 2 pi on 3. And that is the final answer. Question D. Two vertical walls and the floor meet at a corner of a room. One cube is placed in the corner. A solid shape is then formed by placing identical cubes to form horizontal rows on the floor against the walls, or by stacking vertically against the two walls. An example is the solid shape shown in the diagram. The example is formed from 9 cubes. So they've given us an example of what they're talking about. Let n be the number of cubes used to make a solid shape in this way, and then use mathematical induction to show that the number of exposed faces of the cubes in this shape is 2n plus 1. So what we're really trying to prove is that for n cubes, there's 2n plus 1 exposed faces. Okay, so it's mathematical induction. We need to start off with a base case. So what would our base case in this case be? Our base case would be when n is equal to 1, where we only have 1 cube. Now, just think about this. When you have 1 cubed, the bottom face, well, that's going to be covered because that's pushed up, or because that's just, the bottom face is sitting on the ground, so it's covered by the ground. So the bottom face is covered by the ground. And then we have two faces which are covered up by the walls because they're pushed up against the walls. So bottom face is covered by the ground, and two faces are covered or are pushed up against the wall. Well, I should say the walls because it's both walls. So that means that we have 3 faces which are covered up, which means that we have 6 total faces minus the 3 which are covered up, which equals 3 faces exposed. Now think with this induction question, there's not going to be much like algebra or mathematics really going on. It's just a bit of logic and explaining what's going on really with words. So we've got 3 faces exposed. Now does that fit our formula of 2n plus 1? Well, when n is equal to 1, 2n plus 1 is equal to 2 times 1 plus 1, which equals 3. So yes, it does. So therefore, base case is true. Good. Now we need to make our inductive hypothesis, our assumption. So I'm going to write it as inductive hypothesis. And I think it's not a bad idea for you to do the same as well in an exam, because it labels exactly what's going on. It shows that you know the steps of the induction process as well. So we're going to assume that n equals k is true. So what does it mean to assume that n equals k is true? It means that we assume 2k plus 1 faces are exposed for k cubes. Okay, so that was our inductive hypothesis. That's our assumption, and maybe let's label that as star, so when we want to use it, we can just say by star. Okay, because we know we need to use it. That's part of the induction process. So that was our inductive hypothesis. Now, what are we actually required to prove within the process? Well, we want to prove that n equals k plus 1 is true. So what does that mean? That means that we want to prove that there are 2 k plus 1 faces exposed for n equals, well, not for n equals, for k plus 1 cubes. Okay, so this is what we want to prove. Now, we haven't even done anything. We've just stated what we want to prove, and we've just stated our hypothesis as well. Okay, so now let's start off our proof. And I'm actually going to start with my assumption. So suppose that we have k cubes. Suppose we have k cubes. Then by star, there are 2k plus 1 faces exposed. Okay, so this is just really restating our assumption. So we've actually used our assumption. Now this is part of our proof where we're using the assumption. And now we want to add another cube so that we have k plus 1 cubes. So now we add another cube. So that, and maybe it's a good idea to actually say this, so that there are k plus 1 cubes. So now we're making it really obvious to both ourselves and the marker that we do have k plus 1 cubes. Okay, what happens when we do that? Well, let's have a look up at our diagram here. If I was to add a cube next to this one here, so I'm adding a cube here, what happens? Well, when I push it up against the cube that's already there, this one, you can see that this face here is going to become covered by the face of the cube which I push it up against. So we're taking away one of the faces that's already there. But when we introduce the new cube, we actually add 3 new faces, just in the same sort of manner that we started off with in our base case. Okay, so, and this applies wherever we're looking. So whether we put a cube here, or whether we put a cube here, this is the face that will disappear, that one there, or whether we put a cube up top, this face will disappear. So we're always going to lose one face from what's already existing, but then we're adding on 3 extra faces. So how do we word this so that the marker really understands? So we add on another cube so that there's k plus 1 cubes, and I would probably say something of the following. Wherever we add this new cube, it will cover up an already existing exposed face, and at the same time we'll introduce 3 more exposed faces. Okay, so that's basically what we were just talking about above, but now we've put it into words. So what does that mean? It means that the number of exposed faces, so when we had, is equal to the following. When we had k cubes, it was 2k plus 1. But then we added our new cube in, and what happened? We have to subtract one of those faces away, because it gets covered up by the new cube. But then the new cube is also introducing 3 new faces. So this is 2k plus 3. And I can write 2k plus 3 as 2k plus 2 plus 1, which is 2 into k plus 1 plus 1, which is actually what I wanted to prove, right? This is exactly what I wanted to prove. And so therefore, it's true for n equals k plus 1 if n equals k is true. And so therefore it's true by the process of mathematical induction. And that is the end of our proof. And you can see that there's really no algebra whatsoever. This is the only kind of algebra that we had to do at all. Really, this induction question was just a bit of logic and formulating our logic into words. Okay, and that's the end of question D and the end of question 12.